Hi, today I'm going to introduce the calorimetry method to measure the energy change. So first, let's introduce the calorimetry. It's an experimental progress of measuring thermal energy change in chemical or physical change. And our calorimetry method is based on the reaction is happening in an isolated system. And the chemical reaction is the system, and the water is the surroundings or the environment, and the calorimeter is the universe. Furthermore, the heat lost by the system is gained by the environment, or we can represent it by this equation over here, which is Q system equal to negative Q environment or surroundings. And we also use the heat capacity equation to solve for heat loss or gain, which is this equation over here. So Q is represent the heat change, and M is represent the mass of the substance, and C is the specific heat change, and the delta T is the temperature change. And this is a unit of the each. Furthermore, we are assuming that 1 gram of water is equal to 1 milliliters of water, and the heat gain or loss is measured by the temperature differences. So as we now know the idea of this theory, we can move on to the specific problems. So this is the problem over here, where 1 gram sample of rocket fuel hydrogen is burned in a calorimeter which contains 1,200 grams of water. The temperature rises from 24.62 degree to 28.16 degree. And the question is asks us to calculate the molar emphasis of hydrogen. So after reading the question, we can list out some factors the question gives us. So we know the mass of N2H4 is equal to 1 gram, and the mass of H2O, which is the water, the mass of H2O, which is water, is equal to 1,200 grams. 1,200 grams, and our temperature initial is equal to 24.62 degree, and our temperature final is equal to 28.16 degree. And then we can plug this value into the equation I mentioned in the previous slide. So it's the heat capacity equation, which is Q. So by writing this equation, we have to pay attention that this value represents. So in this case, this is QH2O, which means the heat change for water, is equal to mass of the water. We have to label this what's the each values, whether it's for the water or our reactants, so we won't make mistakes. And then times C of water and times the temperature differences of water. So we can plug the value we know into this equation. So mass of water is 1,200 grams, and C of H2O is 4.18 joules per grams times the temperature. So this is the unit for the heat cap. So this is the unit for the heat capacity. And then we times the this is the unit for the specific heat capacity. So we can get this unit from the specific table or search in the internet. And also times the temperature differences. In this case, it's 28.16 minus 24.62. So it's 3.56 degrees. Give us the final value of 16,757 approximately joules. And now we know this is the heat change for the water. We can plug this into the equation. Another equation I just mentioned before, which is the Q system equal to the Q surroundings. So in this case, our Q system is N2H4 equal to the negative Q of surroundings. So it's H2O. And we get the answer of negative 17.757 kilojoules. So remember, we have to convert the unit from joules to kilojoules. And also I have changed it to the negative value since this is represent our system heat change. So next step, the question is asking us for the molar enthalpy of our system. So we need first, we already know the it's 1 gram of our system. So we can use this 1 gram to find how many moles it's equal to. So it's 1 gram of our sample times 1 mole of N2H4 is equal to 32.05 grams, and we get the we get the answer of like the 1 gram of our sample is equal to how many moles. So we actually convert this 1 gram of our sample into moles. So it's equal to the 0.031 moles of N2H4. So in this case, the question is asking the molar emphasis. So we know we have to use the total heat change divided by the moles of our system to give us the molar emphasis. So which means how many heat change per 1 mole. So in this case, our delta H of N2H4 is equal to our total heat change for our system. So it's negative 17.757 kilojoules, which is the value we get in here, and divided by the value we get in here, the number of moles of our system, 0.031 moles, and then we can get the answer of negative 572.8 kilojoules per mole. So in this case, this is our final answer, and this is the molar emphasis for our system for hydrogen. By finishing this question, we can also do a reflection on the question. So it's an exothermic reaction because the heat change for our system is negative, which means our system is losing energy to the surroundings, and the surroundings is gaining the energy. That's why the temperature is rise for the water. And when we're doing the calculations, we also need to avoid to make a mistake. And the area are most likely to make the mistake is when we're writing the heat capacity equation, we have always label what the values for each. For example, it's MH2O. Well, it's not, it's M for H2O, not M for our system, which is N2H4. So we always have to pay attention to this. Also, we have to convert the values we get from the water to the system, which is the heat energy change we get, and then convert it to the system, so it's a negative value. And many people forget to do this step, which make their answer going wrong. Also, we have to remember to convert the joules to kilojoules. And finally, for the strength and the weakness of this method, I would say maybe in real life it's keep losing heat to the environment, and by environment I'm not mean the water, but actually like the outside environment of the calorimeter. So in this case, it's it's not very accurate, but we are assuming whole of this reaction is happening in the isolated system, so it's theoretically perfect. And that's all from my video. Thanks for your watching.